Alright, what we're going to do is look at how to do trigonometry with the fundamental identities of trigonometry. And so these are really fun things to do, but they're like gigantic puzzles. And you'll be given a few different rules, and here are some of them, not all of them. And you add these to your circle cards so that you can reference them while you're working on your homework. And some of these problems can be really tough, so you've got to stick with it and do the best you can. And for every different person that's out there, there's a different way to show how these identities work. So what we're going to do is we're going to work through some of these identities today and follow along with the notes. Every problem's unique and every problem's different. Some of them are hard, some of them aren't, some of them are easy. Some of them are super difficult, but just hang in there and don't ever quit. And if you need to finish copying these notes down and get them on your circle card, pause the notes right now, and then when you're ready, start them up again. So what we want to do is we want to use the trig identities to find the sine of theta and the cosine of theta if the tangent of theta is equal to 5 and the cosine of theta is greater than 0. So this is a little bit different than what you've been doing. What you've been doing, you would say, hey, I want to take these guys and I want to draw a right triangle and find the angle, the acute angle between the x-axis and all that kind of stuff. Well, we want to use our trig identities now, and we're going to use our trig identities based off of the Pythagorean identities, which the granddaddy of all of those is cosine squared theta plus sine squared theta equals 1. Okay? And from this we can get to our tangent, because tangent is what we know. So we need a trig identity that uses tangent in it. And with a little bit of manipulation of the granddaddy of all the trig identities, we get this. 1 plus tangent squared theta is equal to secant squared theta. And this is the guy that we're actually going to use to help us get started. So secant squared theta, what do we know? Well, we know what the tangent of theta is. We're told in our problem that the tangent of theta is 5. So secant squared theta then is going to turn into 1 plus tangent squared theta, and that's going to be equal to the secant squared of theta. Okay, the little bit of math, we're going to have 1 plus 26 equals the secant squared theta. And remember, let's just real quick have a quick refresher on secant. Secant of theta is equal to 1 over cosine theta. So don't forget that little bit. And then what we're going to do is we're just going to, back to our problem here, what we're going to do is we're going to add these two guys together, and we're going to get, already added them together. This should be 25. So 26 equals secant squared theta. Now, what is the secant actually equal to? Well, you take the square root of both sides, and when you do that, you get the plus or minus the square root of 26 is equal to the secant of theta. Well, remember that when we're working this out, one of the things that we need to be aware of is that the cosine is greater than 0. And they tell us right here, hey, cosine is greater than 0. Oh, by the way, what have we discovered down here? We've discovered what the cosine is. And so the cosine is just going to be the reciprocal of the secant. So we found one of our pieces. So I'm just going to come over here and say, hey, cosine of theta is equal to 1 over the square root of 26. Now we just have to find the sine of theta. And how can we find the sine of theta if we know what the cosine of theta is? Well, again, go back to your identities. We're told that the tangent of theta is equal to 5. Right here, tangent of theta is equal to 5. So what is the tangent? Tangent is sine over cosine. So what we're going to do is we're going to look at how this works out with the sine and the cosine. So if I know that the sine of theta divided by the cosine of theta is equal to the tangent of theta, and I need to know what the sine is. Remember, sine is one of my key pieces right here that I need to figure out. Then what I would say is that the sine of theta is equal to cosine theta times tangent theta. Well, in this case, the sine of theta is going to be equal to the cosine, which is 1 over root 26, times the tangent, which is 5. So my cosine of theta then is going to be 5 over root 26. And so we come back over here to our problem, and we just put it in, 5 over root 26. And you'll need to pay attention because some teachers will allow a radical in the denominator, some won't. But this would be a good answer. If you have a teacher that doesn't like the radical in the denominator, then you would just rationalize the denominator and you'll be good. So that's how you do that guy. And again, there's more than one way to work this one out, but using a trig identity, we can do this without using a reference triangle. Okay, so here's another one. If the cosine of theta is 0.34, find the sine of theta minus pi over, or theta minus pi over 2. And again, we want to use trig identities, and some of these guys were on that first page, but look at your circle card, and one of the identities on there that you'll see is that the is using the sine of theta pi over 2 minus theta. Okay? And what we're going to do is we're actually going to manipulate this guy just a little bit and turn him into something that matches our question. So if I look at what's going on with my question, the theta is positive and the pi over 2 is negative. So wouldn't that be the same thing as saying the negative theta minus pi over 2? Okay, and again, if you'll look at your identities right above that, another thing that we can get is this guy right here. The sine of negative x is equal to negative sine x. And so I've got that negative right here. And so what this guy is going to become, the part that we're going to actually work with is going to be negative sine theta minus pi over 2. Okay, that's the guy that we're actually going to work with. And oh, by the way, again, looking at your identities, the cosine of pi over 2 minus theta is equal to the sine. So this guy right here is basically the opposite of the cosine of theta. And since he's the opposite of the cosine of theta, and we know that the cosine of theta is 0.34, then what we're going to do is we're just going to take the negative of 0.34. So our final answer would be negative 0.34. You may need to watch this part a couple of times. Have your trig card handy, your circle card handy to look at your relations. But it's not a horribly painful thing. Okay, we're going to simplify sine cubed x plus sine x cosine squared x. Now this looks like a big, nasty, long, horrible problem, but if you'll notice right here, I've got a sine cubed, and right here I have a sine. So what I'm going to do is factor a sine out. We're going to treat it like an algebra problem, and I'm going to pull out a sine x. And when I do that, that leaves me on the inside sine squared x plus cosine squared x. And if I've got sine squared x plus cosine squared x, guess what? This whole guy over here in black is going to go to 1. So I'm going to end up with my sine x times 1, which is going to just end up being sine x. And that's all there is to that. When you simplify these guys, some of them simplify really, really easily, and that's one of them that does so. Okay, we've got a big one here. Secant x plus 1 times secant x minus 1 over sine squared x. So FOIL out the top. Now, notice that on the top you have conjugates. Secant x plus 1, secant x minus 1. And one thing that will help you in your math, in all of the math that you do, is if you understand that when you have conjugates, there is no middle term. So I can FOIL these guys out, and when I FOIL these guys out, I'm just going to multiply together the first terms, and I'm just going to multiply together the last terms. And that's all I need to do. I don't need to do anything else. And so when I do this, what I'm going to end up with is secant squared x minus 1 over sine squared x. Okay, this is great, but what does that tell me? Well, look at your circle card. Find secant squared x minus 1. It's got to be equal to something. And in fact, with a little bit of manipulation, we can take our 1 plus tan squared equals secant squared. And you can see by subtracting 1 from both sides, I can get tangent squared. Okay, there it is right there with a little easy manipulation. And so what I'm going to do then is I'm just going to rewrite the top as tangent squared x. And then the bottom stays the same. It's just going to be sine squared x. Well, what have I got now? Well, if you're paying attention to what's going on, you can also rewrite the tangent. Okay, the tangent is what? Sine squared x over cosine squared x times my denominator right here. So 1 over sine squared x. Now, if you have the same thing on the top and the same thing on the bottom, you can cancel them out. They divide out. They go away. They reduce. And that leaves me with 1 over cosine squared x. And 1 over cosine squared x reduces us down to secant squared x. And when you're showing your trig identities in these kinds of proofs, you'll want to go to where you don't have any fractions left, if possible. So 1 over cosine squared x we know is secant squared x, and we would go ahead and take that step. All right, another problem. Simplify cosine x over 1 minus sine x and 1 minus sine x over cosine x. So on this guy, what you're going to need to do is get a common denominator. So let's go ahead and multiply the right-hand guy by 1 minus sine x on the top and on the bottom. And let's multiply the left-hand guy by cosine x. When we do that, we're going to get a new fraction with a new shape, and it's going to be cosine squared x minus sine x minus sine squared x. And then on the bottom, we're going to have cosine x times 1 minus sine x. I would not necessarily put the bottom together yet, just in case something will reduce out in the long run. Okay, so look at the top. What are you going to end up with on top? You're going to end up with cosine squared x, and then if you'll notice your minus sign here, you're going to change the sign on this guy and change the sign on this guy. So that's going to give us cosine squared x plus sine squared x minus sine x over cosine x times 1 minus sine x. Alright, so now what? Well, what we're going to do is simplify that top even just a little bit more. And if you'll notice that I've got cosine squared x plus sine squared x. We like this a lot because that's just going to be 1. So that reduces all the way down to 1 minus sine x. So if I've got 1 minus sine x, and then on the bottom I've got cosine x times 1 minus sine x, then I can reduce the things out that are in the top and in the bottom at the same time, and they're multiplying. So the 1 minus sine x has a partner on the bottom. It's 1 minus sine x. And that leaves me with 1 over cosine x. And again, we don't want a fraction as part of our answer if we can avoid it. So this would give us secant x. And again, you're going to have to take a few steps on this one and have your circle card handy and look for things that are equal. We know that cosine squared x is equal to 1. That makes the problem easier. And so you just have to look for those things. All right, here's another one. We want to solve this guy for x on the interval from 0 to 2 pi. So cosine cubed x divided by sine x equals cotangent x. Now, we want to be very careful with what we do because it's possible that through solving this we may introduce things that won't work. So we want to be careful with how we handle this. We don't want to introduce any numbers if we can help it. Well, cotangent x is the same thing as cosine x over sine x. So I have cosine cubed x over sine x. And that's going to be equal to cosine x over sine x. And again, we want to solve this guy out. So I'm just going to cross multiply. Okay, that's a legal thing to do, right? And so that's going to give me cosine cubed x sine x equals cosine x sine x. Okay, and then when I do this, one of the things that I can do is I can move the cosine. I can divide out the sine x. I've got a sine x on both sides, and with that sine x on both sides, then it doesn't matter what's going to happen to my number. The sine x is going to be equal to sine x. So sine x we can lose. Okay, so he goes away. And then that's going to leave me with cosine cubed x equals cosine x. All right. Be careful here because you can't divide both sides by cosine x. That won't work. So what we're going to do is we're going to subtract this cosine x from both sides. And it's going to give us a new shape on our problem, and it's going to look like cosine cubed x minus cosine x equals 0. Now, this factors, and I know it doesn't look like it right now, but check out this bottom guy right here. I've got cosine cubed x minus cosine x, and there's a cosine in both of those. So if I factor a cosine out, that's going to leave me on the inside with my cosine squared x minus 1 equals 0. Now cosine squared x minus 1, that doesn't help me too much. But again, if you go back to the granddaddy of all trig functions and you look at that guy, and it's cosine squared x plus sine squared x equals 1. If I move sine over and subtract 1, I would get this guy. And if you'll notice, cosine squared x minus 1 is what I have right here. So let's rewrite the bottom guy again. Cosine x times negative sine squared x. And we got a stray little negative in there. Let's just rewrite this. Now set each piece equal to 0 and solve it out. And it doesn't matter what you do to sine squared. Whatever sine squared is going to be, wherever sine is equal to 0, sine squared will also be 0. So we're going to look at this guy. And where does cosine of x equal 0? Well, the cosine of x is equal to 0 at pi over 2. And 3 pi over 2. And the sine of x, again, we could work this out if we need to. Take the square root of both sides, and that would give us the sine of x equals 0. Well, where does that happen? The sine of x is equal to 0 at 0 and pi, and we're not including 2 pi here, we're just going up to 2 pi. And so where are the places that this guy can happen? Well, this guy can happen at pi over 2 and 3 pi over 2. Those will both work for sure. Now, check this out. Where I get sine x equal to 0, which is at 0 and pi, we have to pay attention because in my original problem in the cotangent right here, what will happen is if I put 0 in for my sine, if I put a 0 in for my sine, I am undefined. Okay? It's not possible to get that specific number there. I will be undefined. So when we go back and look at our problem, and we look at this where the sine is equal to 0, we have to not allow these, we cannot allow these as part of our answer. So on this particular problem, the only answers that we can use are the pi over 2 and the 3 pi over 2. So pay close attention to your original function so that you understand where you can and cannot have zeros. Okay? Alright, so we're going to find all the solutions for 2 sine squared x plus sine x is equal to 1. So this is a really interesting question. Let's do this. Let's set it up and make it look like a quadratic by subtracting 1 from both sides. And when you do that, you're going to end up with 2 sine squared x plus sine x minus 1 equals 0. And when you look at this, think to yourself, hey, you know what? If I just let y equal sine x, what would you end up with? So what we're going to do is we're going to take everywhere that was a sine x and we're going to let it equal y. And that gives us a different, it's the same problem, different shape. It's going to give us 2y squared plus y minus 1. There should be a squared right here. And that's going to equal 0. So how can you solve a problem that looks this way? Well, you can factor it. You could use the quadratic formula. You got lots of different options. It's actually not too bad to factor. We know that we're going to have a 2y and a y, and we know we're going to have a 1 and a 1. We just have to figure out where the correct signs go. And on this, we want to end up with a positive 1 in the middle of the problem. We want a positive 1y. And so in order to get the positive 1y, 1 times 2 needs to be the biggest number. And so we would put a plus here and a minus here. And so 2y minus 1 equals 0, and y plus 1 equals 0. And go ahead now and solve for y. So we would say on this guy, y is equal to 1/2, and y is equal to negative 1. Well, what does that mean? Remember, we said that y was equal to the sine of x. So everywhere we see y, we're going to set it equal to the sine of x. And it's going to give us a little bit of a different shape on our problem, and it's going to look like this. Sine x equals 1/2, and sine x equals negative 1. So we want to know all the places on the unit circle that this happens. And where those places are, those are where our solutions will be. And so from sine x, for sine x is equal to 1/2, if you look at your unit circle, that happens at 2 places, at pi over 6 and 5 pi over 6. Where the sine is equal to negative 1, it happens in one place, pi. And again, what you want to do is you want to check this in your original function. So go back up here to your original guy and just make sure, hey, do we have a fraction that we need to worry about the domain? Are we going to be defined everywhere? And when we're looking, everything works. So pi over 6, 5 pi over 6, and pi all work. Now, keep in mind that the sign is periodic. And so what we need to say to be a little bit more correct is that we will have answers when x is equal to pi over 6 plus 2n pi. In other words, every 2 pi units, pi over 6 works. Or x equals 5 pi over 6 plus 2n pi for the same reason. Remember, on the unit circle, you go around 2 pi units, you're right back to where you started. Or the last guy would be x equals pi plus 2n pi units. And so all these guys would go together to give you all of the possible answers. And n could be any integer that you need it to be. Okay, so n would be any integer. And that's how you solve this guy out. And it's doable, and just use what you already know about things to help you solve what you don't.